Hi, this is John Buck back with another discrete time linear system video. This video is going to continue on about difference equations. If you haven't seen the video talking about definitions of difference equations and the different adjectives or terms we use to describe them or classify them, you need to go back and watch that video first. In this video, I'm just going to do examples of two difference equations showing how we can use them to find the output from the input when the system is linear and time invariant, and also some examples of how we apply the terminology from last time to these systems. So let's get right to it. Okay, so my first example, y of n is this one shown here. Y of n is equal to y of n minus a y of n minus 1 is equal to b x of n. And the first thing I want you to do, we can think about, well, when we're going to try to find the output from the input, we need to reorganize the equation or solve the equation so that I have just y of n alone on one side of the equation. I have the current value of the output on one side, and then so now this is an equation that says how do I plug in and turn the crank to values of the input and maybe old values of the output to get the next value of the output here. So first question I want you to think about is just practicing with our terms. What is the order of this difference equation? And is this a recursive or non-recursive difference equation? And how do you know? So I want you to pause the video for a second and then think about, again, is it recursive or non-recursive system? And what's the order of the system? And then come back and I'll tell you the answer to those. But take a second to think about it on your own. Okay, so to look at this one, we would say this is a recursive difference equation. And the reason it's recursive is that y of n is defined in terms of x of y of n minus 1. ITO in terms of, right, if I look up here at this equation, this term here on the right-hand side says I need to have old values of the output to find the next value of the output. So that makes it a recursive difference equation. And then to find the order, well, that's the maximum delay in the system for y of n. So if I look at this, the biggest delay is 1. So we'd say this is a first order system. First order system. Because the maximum delay in the system is 1. Okay, so now what we're going to do from here is say, well, let's look at how do we find the impulse response for the causal LTI system with this difference equation. And the way we do it is we say, well, the first thing we have to remember is to find the impulse response. The impulse response is what comes out of a system when I feed in an impulse. Right? So if I take my system, I put in just delta of n, then the output will be h of n. So I can first replace y by h in this system and x by delta of n. So this is saying h of n will be equal to a h of n minus 1 plus b times delta of n. And then the second thing is to remember what we saw in the earlier video about to have a linear time invariant system, I need to have initial rest. Right? Initial rests told me that the output will be 0. Right? My initial conditions are initial rest, which says that h of n equals 0. In this case, for n less than 0, because the input x of n equals 0 for n less than 0. Right, so I have this initial rest condition that says as long as the input's 0, the output will be 0. So I've got all that going up to times. For all the negative times, I know the output is 0. So let's just start working our way forward. Well, using the equation from up above, right, or just above me, this equation right here, right, I can say, I just set n equal to 0. Maybe I'll make some room for that on the left-hand side here. So saying, you know, when n is equal to 0, I get h of 0 is equal to a times h of minus 1 plus b times delta of 0, right? So I've just replaced all the n's by zeros, and now I walk through this and I say, well, I know we just said due to the initial rest, this term is 0, this term is 1. So when I plug those in and simplify, this tells me that my output will be just equal to b, right? I'll have a times 0, which is 0, plus b times 1, which is b. And now I just can iterate forward. I can say n equals 1, gives me h of 1, which is a times h of 0, plus b times delta of 1. Right? So again, just replaced all the n's by 1s, and I get this new equation for the next point in time. So this is what I mean by turning the crank in time. And now I look at this and say, well, h of 0, I just found that. That's equal to b. The impulse at time 1 is equal to 0. So now my output is ab plus b0, which gives me ab. And I can play this game until the cows come home. Right? I can say, well, n equals 2. I just plug in h equals 2. I didn't say it's a very good game, but I can keep playing the game as long as I want until I have all the values I need, or I run out of patience and program a computer to do it for me. Right? So now this is equal to AB delta 2, impulse response at time 2. Well, that's something other than 0, so it's 0. And so I put this together, I end up with a squared b, and so on moving forward. Right? I'm not going to keep going through, but well, I guess I'll do one more. So n of 3 will be h of 3 is a times h of 2 plus b times delta of 3, which is still the second term. This is still 0. And so I get a cubed times b, and so on. And more generally, we haven't really proved it, but we can get a pretty good guess that in general our pattern is going to be, and we'll see later this semester how to show this is true for all n, that h of n will be equal to a to the n times b for n greater than or equal to 0, and 0 for negative time. So again, as we would expect from a causal LTI system, it's 0 for negative time. So that's a good sort of sanity check or reassurance we've got this right. That if I have a causal system, its impulse response should be 0 for negative time. And it is here. Another interesting question is, well, is this stable or not? Is another good question for another day. Let's look at one more example. So here's a different system. Again, y of n is equal to a half times x of n minus 1 plus 1/2 x of n minus 2. So again, I'm going to ask you to pause the video for a second and try to decide on your own, is this recursive or non-recursive difference equation? And what is the order of this difference equation? All right, so hopefully you've had a moment to think about that. And for this example, this turns out to be a non-recursive difference equation. And the reason is, right, we can, y of n only depends on values of the input, right? We don't care about unlike the last example I showed you, we don't have any delayed versions of y of n on the right-hand side here. So we say this is non-recursive. And the order, on this one it would be 2, because the largest delay in the system, I have a delay of 2 here. When I have y of n on this side, I have a delay of 2, so that makes it a second-order system. Okay, so again, now let's go through the same process and say we want to use the difference equation to find the impulse response. So we want to find h of n for the causal LTI system with this difference equation, whose input and output satisfy this difference equation. Well, again, same as we did in the previous example, we replace y of n by h of n. We replace x of n by delta of n. We say that if I want to find the impulse response, I need the input to be the impulse so that the system responds to it. Oop, bad. this second x should be a delta, right? We're setting the x of n to be delta of n. Right, so once I do that, I pretty much have the impulse response here right away. Right, I can sort of look at it if I want and go through n by n, but this is a nice property for non-recursive systems. All I have on the right-hand side are x's. Once I plug them in, once I set x equal to delta, I have the difference equation here. Right, I could go through and say, well, this is just weighted and shifted impulses. So at n equals negative time, it's going to be 0. Up until, this will be the first one, when n equals 1, this impulse is equal to 1, and then it's scaled by a half. Right, so I have a value of a half at n equals 1, and also at n equals 2. And for any n bigger than that, this argument will not be 0 again. So all these deltas would go back to being 0. So this is a non-recursive thing, and we see why we call these finite impulse response systems, right? As h of n, this is my picture of h of n here, has a finite length, and then it goes back to being 0 again. Okay, so those are two examples of how we apply the terms non-recursive, how we find the order of a difference equation, and then showing you how I can use the difference equation to find the impulse response. And it doesn't just have to be the impulse response. If you gave me some other x of n, like a measured speech signal, I could run it through the system in principle just by each time reading the values of x and combining them together, right? I'd say, well, if I want to find the output now, I take x one sample ago and x two samples ago, scale them each by half, and add them together. And so again, as I said in the intro difference equation video, I could do that in MATLAB using the filter command. I would say y is equal to filter of my b coefficients are my coefficients of the different delayed versions of x. So it would be, well, for MATLAB it won't take fractions. So I say I have the first one is x of n, which is coefficient 0. It's missing in the equation. And then 0.5. And then I'd have the a coefficient, or the coefficients of y, which is just 1 here. And then whatever, I'd have to define my input x. It might be my speech signal or something else like that. But I could run this system on any input I wanted by using this MATLAB command, assuming I'd already defined my signal x to be the input before that. So I'd have, just to make that clear, I'd have x equal something up here so that it's already defined, and then I can use the filter command. All right, so that's plenty long enough for this video. So we'll, again, stop here, having shown two examples of applying difference equations, and then the next video is we'll move on to the idea of block diagrams, sort of a graphical language for thinking about how difference equations can be implemented.